minutes because I got this ticket. And like, what's his name was staring me down.
Oh, Tim.
Yeah.
God needs to take a chill pill. No, I got it during after the class in English. Yeah. So it looks like no one cares about this game at all. Oh, I checked homecoming game. We don't have any tests Monday.
Okay, well, which question are we going to pose and us answer? Who we are and what are we doing here? Just in case, make sure that I'm not in the wrong class, you're not in the wrong class. So it looks like this is physical chemistry, which targets what? Prediction outcome of experiments, like NMR, UV spectroscopy, rates, activation energies of reactions. And this is kind of teasing factor. In fact, we are doing quantum chemistry, and more narrowly, we are doing some boring math. But this all should help us to answer posed goal and a sufficient level to give you trampoline for your career, whether it is science, research and development, industry, or teaching. What is the main outcome of today's meeting? What are we going to get? Any suggestions? Based on what we were discussing before, you can make an educated guess. And if you were browsing through any quantum texts or heard about I do not exclude that you will get the right word. So we are going to get one of the major principles that sit in the background of quantum theory, which will be principle.
Uncertainty?
Yes. So how do you formulate it?
Well, there's the space momentum uncertainty principle, which basically says that the better you know where the particle is, like the smaller area that you know it's in, the less you know about its momentum and vice versa. So like the more you know about one, the less you know about the other, just inherently, because there's no getting around it.
You can get out of here if you want to. Did you got what London offered? Not quite, or you've heard something? Position and what? Momentum and what?
Position.
Yes, momentum and position are momentum and position are what?
Observables.
They are observable. Okay, and they are connected. So these two observables have what?
Uncertainty.
Yes. So they both are uncertain. And the uncertainty of momentum and uncertainty of position are what? Connected. So the main message will be that you cannot have both position and momentum certain. In most of the textbooks, it is offered as a postulate or some paradigm without proof. Today we will harvest benefits from our math efforts. So we will get this uncertainty principle as an outcome of the writing long equations. So it will be not given to you as a statement, you will derive it easily. Of course, we cannot derive it generally for any system. We will derive it for this crazy model of a lone electron in the empty universe. But then we can project it to other systems and think that probably it is universal. So we can basically that's it. And now we need just to have a math proof. And I do have a fear. I'm restricted from two sides. There is a chance to deliver this main message in 3 minutes. And what to do in the rest of the lecture. And there is another danger to go into lots of details, starting maybe from some comments about homework, and then being late for the edge of the meeting. But since you get the main meeting, you get main message. Probably you would allow me to invest a little of time about homework, unless everyone is happy and have completed it. Please give some secret signs if you're interested in homework comments. Oh, it's even evidence signs, not even secret. Okay. So we are colleagues. We are on the one side of the trench against the science, against the theory. So me, you, and you between yourself. So I don't mind if you help each other with homework or consult. If you want to stand out of the rest of the class, I will give such an opportunity with a small research project which will be individual for everyone. But since we are on the learning curve on the very simple materials, do not be too competitive. Like, I do not give you a hint how I do it. I want to get a better grade. No. If you ask and tell each other, it will be really beneficial for all of us. And I will give you a chance to stand out, that no one can compete with you. Okay, so what about the? In, out. In, out. It's not cooperation. Okay, it will be challenged for the next time. Zoom in, zoom. Can you zoom out with this remote?
You want to zoom in or zoom out?
Zoom in. Excellent. Thank you so much. Ah, it is our favorite picture. So first, how do you like Fourier transform from the Wikipedia or other sources? Or have you been confused, or you've found connection between question number 0 and the rest of questions? Well, it's better to go over simple things rather than skip them. So, what is Fourier transform? Is conversion of a function of, let's say, x into set of coefficients. So we already do it in quantum theory. And this conversion into set of coefficients is by say from minus infinity to infinity in some limits, right? And escape sine with the same argument 2 pi x and somewhere t x. So there is a way to convert a continuous function into set of discrete coefficients, encode, right? And then send a telegram to a friend like, here is the set of the coefficients, guess which function I processed. And based on the set of these coefficients, where n goes from like 1, 2, 3, and you can drop the series early enough if it is a good function and you are a good mathematician. So you send, instead of function which can be complicated, in Excel you like need whatever, few hundreds of points to have a continuous function. But if you expand it into these numbers, then you just communicate like handful of numbers, and you can reconstruct function back, and it will be very, very close to whatever we have, right? Of course, there are some limitations. This is for periodic functions, and there are they shouldn't. Well, if you would be mathematicians, we would set up set of boring restrictions like no division by zero in the function, no spike, something like. Good. I anticipated his answer on the number 0. It is what? 2 lines. Summarize in 2 lines. Right? Fourier transform. Of course you did so. Now, and you still bring homework. It is not the key. I leave you some room for creativity or to make mistakes. For example, I skipped the coefficient 0. It will be your minute of glory. And if you have these functions, a and b, then you can reconstruct your original function as summation. Is there a chance? Hello? Is there a chance to move this image to left bottom? Thank you. So you can represent your function as a summation of sines and cosines of different arguments with this expansion coefficient. So it is a useful trick. And now with computers are being so quick and so powerful, we do not care much. But whatever, how many years ago, in 18th, 19th century, if we are French scientists living on different continents, and we want to send a postal dove with a function, you cannot roll too many numbers or make much drawing. But if you make up a couple of coefficients, it is condensed information that you can pass on. Okay? So, is it sufficient for doing number 1, or you want more coefficients? Give me a secret science. Do not hesitate. It will not. Thank you so much. It will not damage your chance for creativity. Is it clear enough? For some, yes. Anyone wants more coefficient counts? No? But I want to give a count. So your function is periodic. If you go to L, 2L, 3L, you see it is the same. Therefore, we will use the same. Instead of integrating from minus to plus infinity, we will integrate from 0 to L. And some of you were talking to me in private, and I was lying. Well, not lying, not deceptive intentionally, just forgotten. Same idea as when you do expectation values. You need to normalize. So there should be a coefficient 1 over L in front. And then you can put anything in front and at the end, like A, 1, or whatever, equals. Then you plug in the function, and then you do first of the cosines. Instead of n, you plug in 1, x divided by L. Almost done. One more command. the function is 1 up to L over 2 and is 0 after, right? Therefore, this integral can be split on two integrals from 0 to L over 2, blah, 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 plus integral from L over 2 up to L, blah, 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 right? Which of the integrals will be 0? First or second? Second, yes, yes, because on the second interval the function is 0, so everything is multiplied by 0. So you take only over the half of the space. Okay, this should be sufficient to complete it. Is it clear about the question number 3, more or less? Yep. So it's very similar to what we did in class. You let me go? Not from the class, to the next slide, right? You don't want comments. Just identify full square, bring this into the shape of e minus y squared dy from minus infinity to infinity, which will be equal to square root of pi. And as a price of change of variables, identifying a full square, you will get some normalization, which will be exponential of some combination of the things. And they actually will be the answer, because this integral of Gaussian integral is trivial. So you bring it to trivial shape, and then see whatever comes as a factor on the front. 2x squared p sigma e to the power minus, not x, it will be k squared sigma squared divided by something like 4 or 2 or yeah. But sigma, which is very interesting, the sigma here goes not to the denominator but nominator. You'll find it, like in the x space you have sigma in the denominator of this exponential. Here, if you do it carefully, it will pop up into the nominator of the exponential. Enough. I think you're well equipped to complete it. I did it this morning as an exercise, and it took about 40 minutes. So for one single run. Of course, if it is a failure, then one needs to do it over. But, what else? You can also arrange a system of extra credits for bringing homework early. If you think like, if you don't need any comments, you can do it at evening when it is assigned, bring it in. If you're interested. Those are so little things just to help all of us to get through a bigger chunk of material. Okay, where did we stop last time? And what was our goal? This is probably right, but too boring, and you may have seen it in the recording. Okay, I have kind of summarized where we stopped on this little piece of paper. I will give a little reminder, introduction, what we are doing, what is our goal, so that it will be not a shock to dive into math right away. And the main message, the uncertainty relation, it is something really simple. We already debated it, discussed it verbally, and it will be maybe one slide with a simple picture. But to get to it and to feel ourselves independent derivers of equations, we need to suffer. So we have got a third way to do what with future? To predict, yes. And in order to go through this way, remember there was a simple quiz, not for you, for me, to see how you go through. That takes into 3 components: eigen functions, eigenenergies, and expansion coefficients. When we sum or integrate them together, we get the future. Remember? Something like this. Okay. And if we do it for our poor alone electron in the space, we take expansion coefficients from answer of last question of your homework. We have eigenfunctions as a plane waves, like oscillations in the space, and eigenvalues of energy will be same as in normal science before quantum. P square over 2m with understanding that P is h bar times k. This whatever index wave vector dimensionless momentum. Good. And then we did several manipulations because this integral that we were standing in front of, if you have a lot of wild imagination, one can identify a Gaussian function there. And one can identify Gaussian integral there. So integration goes from minus infinity plus infinity. And argument, it is a polynomial of second power, which means one can identify the second power of some variable that is composed of everything that we have. Right? So the technical thing, how to get to this Gaussian integral, is three principles. Right now I'm not doing my job. It was something from math courses. So to identify full square, you need to find a square, b square, and 2a times b. And if you're towards going to your goal, you are missing something in your expression. You can multiply any term by factor, but as a price word, you divide by the same factor. Right? And also, if you're missing some term, you can add it, but as a price word, you immediately subtract. And when you do such manipulations, you can come up to very appetizing expressions that can be easily convoluted to something reasonable. So here is our full square that will be later placed as this integral. And this term that came up from adding and subtracting, and this factor that came from change of variables, but save time. You will do similar exercise in your homework. Come into here and there. So in fact, the integral gives trivial part, and then we need just to pull what are those terms. So from now on, or next minute, we'll stop being mathematicians and we'll become chemists again. So we will start scientific analysis what we have here. Okay. So B lowercase is this animal, and we need to plug in this A coefficient to the denominator and B coefficient colors to the denominator. Okay. What are we going to get? Well, let's maybe rush through, but I just give a little snapshots how we do it. So the factor in front, of course, it is important if you do it for the grade, but not in the class. For our major answer for our scientific analysis, right now we can temporarily skip it and focus only on this factor. Now, B is minus ix. and we need it squared. So x squared clear, I squared minus 1. So it will be e to the power minus x squared. And in the denominator, upon taking the square, we have 4 times a minus sigma 0 over 4 minus I h bar 2 masses times time, close the bracket. What do we get? It's our future that we have predicted. X, comma t. One more beautiful colors. And we multiply it by some constant, which we don't care right now. So we are ready to do science. What can you tell about redraw it so that it doesn't interfere with this little exponential? And this whole thing is in the power of exponential. So let's analyze, let's think about this function. What does it tell to us? First, interesting. See, this 4 can cancel with this sigma, which is good. So how does it compare with our initial condition? So there is a simple sanity test to self-correct. And I need to be first in doing it all the time because I'm doing it all the time. It's so easy to forget plus, minus, a factor. So one needs to have some way to check it. So when we were scientists last time, we did agree that our main question is to see whether electron will expand or shrink. And in order to test this hypothesis, we set up initial condition as psi 0 equals e to the minus x square here, divided by sigma 0, right? Gaussian function. Good? Then I have invited you to believe me, which formally you do not need to. You may just check and require me to prove each step. But this was wave function at time equals 0, t equals 0. And now I want you to believe that we have the future, wave function at any time in the future. But if our solution is correct, then if you plug in time equals 0, we should get back the initial condition. Well, if time equals 0, then in the denominator we have only this sigma sub 0, right? I think there should be pluses. Yes, now everything is clear. Good. So by plugging in time equals 0, we reconstruct back initial condition, which means that there is always chance to be wrong, but probably not this time. Are you happy with this function? Do you look at it and become happy? Some of you do. Partially. I'm not yet happy. What makes me unhappy just as a user? If I hire a mathematician and he brings me this function. What do you want me? How do I plot this imaginary unit? I want probability distribution and you give me some function. So this imaginary unit it could be correct, but it is not convenient for intuitive analysis to think in the complex plane or whatever. And you are certified experts in postulates of quantum mechanics. You taught me something about probability, wave function squared, right? So the meaning is not, the physical meaning is not behind wave function. It is only in the wave function squared and expectation values and eigenvalues.